Alright, I'm not sure where the last one cut off, but anyhow, let's do this with the Lewis, or sometimes it's called Lewis dot structure, or as your book calls it, the dot structure. So this and this are the endpoints which are derived from the Lewis dot structure. So let's start with that. So sodium was in group 1. So oops. So it has 1 dot, and chlorine is in group 7, so there are 7 dots. Remember, you're imagining a box. Alright, and notice there's one electron missing, or not missing, but there's a space for an electron for the chlorine. And so what happens, this is how you draw this, is this one outer electron of sodium will go right here. And so what happens after that, of course, that's when you get the charges. So the sodium becomes +1, and then the chlorine is -1. And because of this, the fact that there's one sodium and 1 chlorine, then they will stick together as this, and so this is NaCl. Okay, whoops, that's supposed to be an L. All right, and so here, let me write it over here. So it would be NaCl. And so the way that you would say this is you name the metal first. So you write the word sodium, and of course you'll have a periodic table, so you can just do that. And you don't say sodium chlorine. You say, now that it's in a bond like this, it's sodium chloride. IDE. And that's an important suffix, that IDE. You have to include that when you do these kind of things. All right. So when it's a metal and a non-metal, you always end in IDE. All right. There's going to be some exceptions to that when we get to the polyatomic ion chart, but I'm already getting ahead of myself. Let's do another example. So with the next example, I'm going to use potassium, so that's K, and let's do sulfur, which is S. All right, so potassium, you guys can look this up yourself. Potassium, of course, is in group 1, so it gets 1 single dot. All right, and the sulfur is in group 6, so it has 6 outer electrons. Right, and so there's 4 of them, and then there's 1 lone electron, and then there's 1 lone electron. Okay, on in the imaginary box. What's going to happen is this potassium will give up the 1 electron, and it'll come here to match the lone electron. But so the potassium is now happy. Basically, you can kind of think of it as it's met its octet rule. That's what I mean by happy. And you always have to imagine that this is some huge solution where there's lots and lots of potassium, lots and lots of sulfur atoms floating about and interacting. And so you can imagine another potassium with its 1 outer electron. And so what's going to happen is that electron will go right here, and now the sulfur has 7 outer electrons, so it's met its 8 outer electrons, and so it's met its octet rule. And so you can actually see, I mean, you could right now write out what the molecule is going to be. Notice there's 2 potassiums for 1 sulfur, so you write it like this: K, and you write the subscript 2 because there's 2 atoms of potassium, and the sulfur there's just one. And you don't ever write the one as a subscript, that's just implied. So this would be, this K2S would be called potassium. Here, let me write it out. Okay, potassium. And it's, the S is sulfur, but it's not, you don't say potassium sulfur, you say potassium sulfide. Sulfide, IDE, right? We always end with that suffix. It's an S. You always end with that suffix IDE. So this IDE comes from the fact that this the non-metal here is on the periodic table. All right. So there's another example. Let's try to do one more. Here, I guess I should take a quick look at the periodic table. Here, whoops, where's my periodic table? There it is. All right, so with the periodic table, I'm just gonna pick two here. So notice I'm not picking anything from the transition metals. You really, it would not be good to do that. Here, let's do. How about aluminum, which is the only group 3. Like these are transitions down here, or not transitions. These are, yeah, I'm sorry, they are transition metals. So aluminum is the only group 3. It is a metal, and let's do aluminum with oxygen. So, well, yeah, why not? Aluminum and oxygen. Okay, so aluminum's group 3, oxygen's group 6. So, so let's get back to our picture here. Whoops, where is it? There it is. So aluminum has 3 outer electrons. Right? So we got 1, 2, 3, and we're going to do oxygen. So oxygen has, of course, 6. So 1, 2, 3, 4, and then there's a lone electron, and then another lone electron. All right, so this is going to get a little complicated, but I always like to start over here on the left, get rid of that electron first, because I don't want to cross my lines here. So the first electron goes there. The second electron is going to go here, and the oxygen has met its octet rule. But notice the aluminum still has one more electron to give. So the oxygen. So imagine there's another oxygen floating about, and this aluminum is going to get rid of that last electron right there. So the aluminum is now met its octet rule, but the oxygen, this second oxygen, needs one more electron, so that's going to come from another aluminum atom. Aluminum you always start with 3 outer electrons because it's in group 3, and that first electron is going to go to that that second oxygen. So now there's 2 more electrons around the aluminum. We got to get rid of those. So we imagine another oxygen, and the first one goes here. Oops, I didn't mean to cross the lines. And the second one goes there. And so now we can write, what aluminum oxide is. So aluminum oxide would be, well, how many aluminums do we have? So you just write Al, and there's 2 of them. And for oxygen, of course, you just count them. There's 3. So that is, let me state this too, even with, the potassium sulfide, we're creating neutral molecules. It's really important to understand that these are neutral molecules. So this would be aluminum oxide. So here, let me write that. Aluminum oxide. Okay. All right. So what we just did with the dot structure, there's actually a much simpler way of doing that, rather than drawing out all of those, individual electrons and so forth. And I'm going to show you that in just a little bit. You know, here it is with the dot structure again. All right, so that doesn't really help us at all. Okay, here it is again. Here's calcium and fluorine. So you know, one of the electrons goes to that fluorine, one of the electrons goes to that fluorine, and so this would be you know, one calcium and two fluorine, so it would be CaF2. So that would be calcium fluoride, right? So you say calcium fluoride. Let's actually use calcium fluoride here in our example. So what I'm going to do now is switch to what's called the crossover technique. So remember, we just found that, you know, calcium fluoride, just from the example in the PowerPoints, was CaF2. So that's calcium fluoride. Okay, so you know, you write it out like this: calcium oh, there's a U in there, that's right. Fluoride, IDE. Okay, so this is the way you write that molecule. This is the way you would draw that molecule. Okay, so let's use what's called the crossover technique. I think this is a good example to do that with. So calcium, you just start with the fact that calcium is in the representative group 2. So calcium would be, to meet its octet rule, would lose 2 electrons, so it would be charged +2. And fluorine is a halogen, and so it gains 1 electron to meet its octet rule, so it's going to be -1. And by the way, we don't ever draw you don't write the 1, just like the subscript of the calcium here in the molecule calcium fluoride is not a, you don't, it's implied that there's a 1 there. Okay, so the way the crossover technique is you use the charges in a crossed over manner. So here so we'll write the 2 atoms next to each other like so, and then basically the crossover technique means the 1 goes with the calcium and the 2 goes with the fluorine. So we're going to put a 2 right there. All right. Let's do another one. How about what we did before, aluminum oxide. So aluminum is group 3, so it's going to be a +3, and oxygen is -2, right? Because it's group 6, so you need 2 additional electrons, and so you do the crossover technique, right? And so the Al. That's here. Let me put the oxygen in here. So Al. So the crossover technique tells you to put a 2. You don't ever put the pluses or minuses as the subscripts, because what the pluses what the subscripts are doing here. These subscripts are telling the number of atoms to create a neutral molecule, a molecule that's not charged. And of course, using the crossover technique, that'll tell us what to put as the subscript of the oxygen, which is a 3. So this tells us this is Al2O3. And that, of course, we got this before using the dot structure, which can be kind of involved because you got to sit there and count all the electrons and make sure it all matches up. But this crossover technique is very simple, and as long as you're dealing with representative groups, it's fairly easy. Okay, so let's do here's a really important one. Actually, I'll start it on the next video.